So this next chapter, problem solving with recursion, or next section, I'm going to skip over because this Towers of Hanoi, we're going to cover this in Wednesday's or Tuesday's lecture. But it's important because what we're going to do is we are going to, I just want to get us here to the backtracking section, which is a different type of problem solving with recursion. Now, and is one of the most powerful ones for solving problems. We've kind of done that, just we didn't use recursion. We did the whole backtracking process, or you're working on it right now when you're trying to solve the maze, where basically you go until you hit a dead end, and if once you hit a dead end, you back up and try another solution. Now, backtracking is essentially a much more powerful version of brute force. Essentially, it's a lot more systematic. It's a systematic trial and error for finding a solution, right? It even says the example is to try to find a path in a maze. If you're attempting to walk through a maze, you walk down a path as far as you can go. Eventually, you get to some dead end where you can't get any further, so you back up and find a new path to go. So it's systematic and it's non-repetitive, meaning we're not going to try anything. We're not going to try something twice. If it doesn't work once, it's probably not going to work twice. So if we never try the same path more than once, right, then we'll eventually find something that exists. We'll find a solution if one exists. So the way we work on these, and again, the algorithm, the generalized backtracking algorithm, I give it in kind of a board and choices for each part of the board. But problems that you can do in backtracking, they're basically a set of choices that you can make. And recursion allows us to basically do this backtracking fairly straightforward. Rather than pushing things onto a stack, we just do method calls. And that method call and automatically pushes stuff onto the stack, and returning from that method call, or closing out the method call, ending it, will automatically pop the stack for us. So let me just go ahead and demonstrate, talk about the problem, one of the problems that we have in that we're going to be doing for homework to make it much more, make it much more, down to earth, real life. So what we're going to go and solve this this homework is Sudoku. Now, for those of you who don't know, a Sudoku board looks like this. Okay. So let me explain the rules to you. Sudoku is a game where basically we try to fill this grid with all the right numbers, right? Now, and the way this works is that we want to fill every row and column. We want to fill every square with values from 1 to 9. And the rules are, I can put in each row should have the value 1 through 9 exactly once. So I can't put another 1 there. See, it lit up red for me, telling me I couldn't put another 1 there. Can't put a 5 there because there's already 5 in the row. Can't put a 6 here because there's already 6 in the row, right? I can however, let's see, I could put a 4 in this row and in this column because there's nothing in this row. Now, similarly, I also have to make sure that not only can't I put the same two values in the same row, can't have 2 4s in a row, I also can't have two numbers that are the same in the same column, right? So 7, right? So same column, can't do that. And the final constraint for Sudoku is I can't have the same value twice in a 3x3 square, right? So notice how this 9x9 board is broken up into squares that are 3x3, right? So the correct way to solve a Sudoku solution means that I essentially have to make sure that I've got all the values in 1 from 9 in each row and each column, and every single row, every single column, and every single 3x3 square contains the values 1 through 9 no more than once. So there's a bit of logic to this, right? So let's just go and see. A bit of logic to this, like saying, okay, so I can't put a 5 here because there's a 5 there. But I can put a 3 here because there's not a 3 here, right? And then I could put a 1. I can't put a 1 there, but I could put maybe a 2 here, maybe a 4. Nope, can't put a 4 there. But what can I put in? 7? Nope. What about an 8? Yeah, can't put there, so that doesn't seem to be a good solution, really. What about here? I can put a 4 there. Can't put a 4 there. What number am I missing? Right, 5, 6. I'm missing a 7, so obviously what I'm doing here won't work, but maybe what I can do is put a 7 here and a 3 there, and I've got my, oh, nope, can't do that, right? So, 3 and 2, there we go. So you fill up something with the row. So you fill up the row, and now we just try to work it out, and basically you try to do one row and column at a time. And there's a bit of logic here that works out. However, logic is a bit hard for your computer, so we'll essentially, the way we are going to write our Sudoku solver is that actually this is a pretty small board, right? There's not too much here. So so what we can do is we can use our backtracking solution here. And the way that works is that basically we will just simply go from one square to another square. So we'll start here, and we'll fill up, and we'll get a good answer for this square. Then we'll go on to this square. Then we'll go on to this square, this square. So we'll go from square to square and fill each up with a number. And when we hit a dead end, where we can't get any more, we're just going to go ahead and back up and start changing the values and then go forward again until we get to the end. Allow me to demonstrate, right? Rather than actually doing something and thinking about this solution and, because we're using our brains for doing stuff like math right now. So might as well do something simple here, right? Can't put a 1 here, right? Can't put a 2 here. Can't put a 3, so I'll go on to the next grid. What about, can I put a 4 there? So 1, 2, 3, 4. Can put a 4 there. Okay. 1, 2, 3. 1. Oh, I can put a 2 there. 1, 2, 3, 4, 5, 6, 7, 8, 9. Can't put any values there, so I'm going to delete that and back up. So I'm going to start from the choices I was making here. 3, 4, 5, 6, 7, 8, 9. Can't put anything there, so I'll back up. 5, 6, 7, 8, 9. Boom. Can't put anything there, so I'll back up. 4, 5, 6, 7. 4, 5, 6, 7. Okay. 1, 2, 3, 4. Oh, 4 there. 1, 2, 3. Oh, 2. 1, 2, 3. Found it, so we'll go on to the next square. 1, 2, 3. Oh, 2. Go on to the next one. 3. 1, 2, 3, 4, 5, 6, 7, 7. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 3. 1, 2, 3, 4, 5, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, I'll have to back up. Delete this. 6, 7, 8, 9. Oh, got another row down. And so on and so forth until we complete the entire puzzle, right? Anytime we get to a dead end, right? 3, so 1, 2, 3, 4, 5, 6, 7, 8, 9. We back up to the square that we were at previously and start from where we were, 4, 5. So the way this works is essentially that each square is, so if we look at our homework, let's take a look at the algorithm that we're using to solve it. Document, so home, teaching, data structures, assignments. Let's go ahead and see. Right, recursion. Okay. So if we look at this, essentially this is the recursive algorithm that I am actually following to solve this problem. So solve board position. Now board and position are abstract. They represent, I don't know what your board is, nor do I know what your position is. I don't know what those mean. But your position is somewhere in the board. Here, position would be actually two variables, right? The row and column that I'm actually at. Right, in the 8 queens problem, we actually have only one position, which is one column at a time. Because we can solve one column at a time because no 2 queens will be in the same column. So think about that when you start working on that. But so position really depends on the problem. If position is such that there's nothing left to solve, return true. So the Boolean here is basically, did we find a solution versus we didn't find a solution. Return true if we found a solution. So here, if our position is such that we've got nothing left to solve. So if we got here, we solve this square, and then we call solve on this square, our position's out of bounds, and for once in our life, getting to out of bounds was a good thing. We're done. Okay, so that's our base case there. So now our recursive case, for each possible choice, this is going to lead us to a recursive case, so it's a bit weird. So for each possible choice, here, a choice is just simply what can we put in the square. So we simply, for each possible choice, if the choice is valid, well, 1 isn't valid, 2 isn't valid, 3 isn't valid. Okay, 3 is valid. What do we do now? If it's a valid choice, we put that down. We put 3 down. We keep it there. Then we call solve board, same board that we're working on position plus 1. So whatever position plus 1 is, which is over here. And then we do the same thing over here. Okay, now here's the catch. Now, if solve board, comma, position plus 1 is equal to true. Okay? So essentially, if I call this square, and it calls this square, and this calls square, and so on and so forth, right? And we get all the way down to here. And if this one returns true, and this returns, so that will return true to this, which will return true to that, 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 right? Because if the person I call, what I'm basically saying is, I've solved my square, okay, it's up to you guys to solve the rest of the puzzle. And if they get back to me and say, hey, we solved the puzzle, I'll be like, great, I can tell the person who called me that I've solved the puzzle and claim all the credit. So, again, this is kind of super lazy programming. So if solve board position plus 1, if calling that one works, then it works. Otherwise, if it doesn't work, right, we get back false, then we don't end up doing anything. So let me go ahead and, right, if we're here, right, so what happens basically if I go through if I get false back? How do I get all false back? Well, I go through all possible valid choices. And if none of those, if me calling the next thing on the board doesn't return true, well, I'll eventually go through all my choices and I'll continue with the rest of this block, which says, which says to clear anything that I marked down over here, like that 9, and then return false. So now 3 gets false. Just, this cell that I was on, it just got false back. So it knows, okay, I can't return true, so I'm going to have to go to the end of this if statement, right? Now to the end of this for statement and go to the next part of the for statement, which means now I go into the next choice. 5, call the next square, and so now that will call the next square to, right, and so on and so forth. Now, what about these empty squares? Well, if you're on a square that's already filled, that already has a number in it, I'd put maybe an if statement over here that says, hey, if the square already has a number in it, go on, call solve on the next square. Now, this is a generalized algorithm. This is a generalized algorithm, meaning this is something you adapt to whatever you are currently working on. This algorithm that I've got down here, it will work for generally anything that you're solving with backtracking. It will work on mazes. It will work on these chessboard problems that you've got. It will work on the Sudoku problem we've got. Now let's go ahead and just talk about this one. There's a nice big extra credit thing here for your Sudoku solver. Okay. And that's a really nice thing. And then I'll make a separate video going over the 8 queens problem, even though I think I've fully described it there. So Sudoku, right? It's, again, another thing. So do Sudoku, by the way, Japanese meaning number place. It's a popular puzzle. Of course, Euler gets credit for it because he gets credit for everything. So the idea here is that we have an input puzzle. Here's a correctly filled out puzzle, right? So now we've got over here, now what they've got is they've got this a file called Sudoku Txt, and what it contains is a file with a bunch of Sudoku boards. And the idea here is that for your extra credit problem, you want to take these boards and you want to solve all 50 of them. There's 50 Sudoku boards over here. So rather than solving one puzzle, you're going to solve 50 puzzles for your extra credit. If you're just doing the normal credit, all you want to do to prove that it works is put in, find a something like world's hardest Sudoku puzzle ever, and copy the contents of that puzzle into your code, right? As like a 2D array. I'd suggest like storing these things as 2D arrays. But for this one, what you want to do is you want to solve these puzzles, and what you do to prove to solve them is you take this number over here, 483, right? And so you take this number from each puzzle, so 483 in the top left, so whatever's top left over here, this number over here, this number over here, and you add all 50 of them up. They're all 3-digit numbers, you add them all up, and then if you create an account on a Project Euler, you will be able to check your answer, what answer you get, to prove that you were able to solve all 50 puzzles. Show that to me, and you will be able to get your extra credit there. So, alright, so I will make one more video on the 8 Queens puzzle.